Hello everyone, and welcome to a short video with a couple examples of how to run binomial and Poisson distributions. I know it looks like poison, but I believe it's pronounced with the French pronunciation of Poisson, but who cares? Anyhow, I'm going to show you how to do these with SAS, because I know a lot of you are using SAS. I'm also going to show you how to do it very easily in Excel, as well as a TI calculator. These are just two standard kind of basic questions that I chose. You'll see questions similar to these in whatever class you're in. So let's start with the first one. So we've got the quality control department examines all the products returned to a store by customers. An examination of those returned products yields the following assessments: that 5% are defective and not returnable, 45% are defective but repairable, 35% have small surface scratches but are functioning properly, and then 15% have no problems whatsoever. All of those details are important because they're going to ask you to calculate probabilities using words that might use one of those categories or two of those categories or three of those categories depending on how they describe the item. Okay, so it wants us to compute the following probabilities for a sample of 20. It's always good to keep track of all of these numbers, right? So we know we have a sample size of 20. So the first thing I'm going to do is I'm going to write down the fact that I have a sample size of 20. Next, we determine, what kind of situation we're working with. Obviously, we know we're dealing with a binomial distribution because I said so at the beginning of the presentation, but how do you recognize a binomial, right? What are the rules of the binomial? Well, you have to have a fixed number of trials, and here we have 20, so check, right? A trial is thought of as a single observation, and we've got 20 return products, so there's our 20 single individual observations, so check, check. The trials must be independent, and what that means is the outcome of any individual trial doesn't affect the probabilities in the other trials. So in this case, because we have a set percentage of things being defective, every single thing coming down the assembly line or coming, returned by customers has the exact same probability of being defective or having no problems and so on and so forth. So the probabilities remain the same. Therefore, the trials are independent. Each trial must have all outcomes classified into two categories. We normally talk to those as being successes or failures. So that's where the binomial comes from, is you have to have only two options. And you can see that all four of these questions ask kind of a yes/no question. So all of the 20 products have some type of problem. So either they have a problem or they don't have a problem, right? You can't like kind of have a problem. So there's only two outcomes. So yeah, it fits into that. And then finally, the probability of a success remains the same in all the trials. Well, we kind of talked about that, but again, because we have a large group and these percentages are set to be constant, that every single thing that we grab or gets returned is going to have a constant, right? Their probability is going to remain constant. If, for instance, we were asking what's the probability that they have no defects at all, well, that's going to stay a constant 15%. Or what's the probability that they have some small surface scratches but are functioning properly? That's going to stay at a constant 35%. So it satisfies all of the necessary ingredients to be a binomial distribution. So some things, just some verbiage so we know what we're talking about. Um, a probability of a success, we normally talk about that as being a p. So little p is just a probability of success. And remember, success doesn't have to be a good thing. Success is just a thing we're testing for. So in this case, we're testing for some type of problem, right? Which obviously isn't a success. And then probability of a failure is really just a complement, right? It's 1 minus p, which we often label as q. Because again, there's only one or the other. So it's got to be p plus q has to add up to 1 because that's how probabilities work, right? We already have n as our sample size. We normally let x equal the number of successes in our trials. And those are going to be all of kind of the nomenclature, jargony stuff that you're going to see in these types of things. Okay, all of the 20 return products have some type of problem. So we know that n is 20. We also know that x is 20, right? So for A, we have n equals 20, x also equals 20, because all 20 of them have to have some type of problem. Well, what classifies as a problem? 5% are defective and not repairable, that's a problem. 45 defective but repairable, that's a problem. 35% have small surface scratches but are functional, that's a problem. And 15% have no problem. So it sounds to me that our P in this case is going to be 0.85. Because if you add up all the problems, you get 85%, or if you just take 15 away from 100, since they all have to 100, then 85% of them have some sort of problem. Okay, so now that we have all our bits and pieces, we can calculate Q, which is obviously just the 15, because it's always 1 minus P. And now if you know how to use the formula, you can use the formula. It's a pretty easy formula. Just so we have it, the formula is, I'll put it over here, probability of a certain number of successes is n factorial over n minus x factorial times x factorial. Then you have times p to the x and then q to the n minus x. And that's how you would do it by hand. Or maybe you want to do it with some technology, make your life a little easier. So how about we try SAS first? Because that's the one that seems to give people the most trouble. Okay, so what I've done here is I have opened up just a basic SAS code window. Go into your task and utilities and just run something simple, then click the edit button, then delete everything, right? And then put in what you want and then save it. I saved this as my own code. This is going to be my probabilities code. As you can see, I titled it probabilities code. And if you now go to your server files, you can see that here are all my data files, and then here's my SAS code file. So I just double click that, this bring this back up, and it's a quick, easy way to always do this kind of stuff. And then you can just start creating a library of things that you have to do by code, right? Because SAS Studio can't do everything point and click. Some things you have to do by code. Okay, so the first one we're going to do, you'll notice that I've labeled this is for one outcome. So this means that this is a binomial when we just want to know the probability of one thing. And by one thing, I mean they wanted all 20 to have a certain, thing, right? So all 20 successes. If they said what was the probability of 4 or more, right? Or less than 10, oh, fantastic. What perfect timing. Uh, you would have to use this one down here, the CDF, right? So the PDF function gives you the probability of one specific one. The CDF is a cumulative one, and it's always X or less. So we'll talk about how we have to augment those things if we need to. Okay, but this one was easy. Our N was 20. Our probability, right, of a success, 85. In this case, we're calling M is our X, right? So M is our number of successes. And that was also 20. Now I'm going to run this and we're going to get a bunch of extra stuff just because I have a bunch of extra code down here. But there is my probability, right? It says N20, M, which is my X, is 20, P is 85. By the way, you could rename that X if you want to. And get the same thing. In fact, if you go into your code, you can just delete all of this and just put the numbers in here and just know that the order in which you put the numbers is X, right? Number of successes, probability, sample size, and then just run that and you don't have to deal with all of this. Either way, you can see there's our probability, 0.038, blah, 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 right? Okay, if we want to do the same thing in Excel, I created a bunch of easy, simple things here. The basic code in Excel is binom.distribution, and then it asks for a bunch of things. It asks for, the first thing it wants to know is your number of successes. Then it wants to know your number of trials, your n. So basically it's asking for x, and then n, and then p. And then if you put false here, that's where you get the binomial PDF that we did in the previous example. That's where it gives you the probability of exactly one case. If you put true, that gives you the CDF. That sums everything up, but from the low end, right? So it's everything from that number and lower. So for instance, let's put this where we want. We need 20 successes out of 20 trials, and there's our probability. You'll see that this changed automatically because I just defined it. You can see it up here. It's just 1 minus C4. I'll make this a little bit bigger so you can see it. And now, here is our answer for exactly that many, 3.8%. And if you remember what we got over here, 0.03, right, 3.8. So the same percentage from both of them. If you want to do it in your calculator, and for those of you that don't care about certain things, just fast forward to the parts where I'm telling you how to do it and the ones that you don't care. So it's second vars, which brings up your distribution menu, right? And you're going to need to scroll down until you get to the binomial PDF, right? Hit enter. If you have the fancy calculator like this, it's going to ask for number of trials. That was 20. That's your n, right? Your p-value, 0.85. X value, that's your number of successes. And then you hit paste. Now, if you don't have the fancy calculator, what it's going to do is it's just going to put this on the screen without the numbers. It's going to put binom, PDF, an open parenthesis, and then you have to type everything in the correct order. And just like with Excel, the first number you give it is the number of trials, sorry, the number of successes. Oh, darn it. I can't remember. Hold on, let me check. Okay, so I just double checked it, and it is number of trials, n. It asks for n first, then p, then x, the number of successes. Okay, so that's how you would do it in the calculator, and you can see that again we got the same results. Okay, well, how about B? A little different. Exactly 6 of 20 return products are defective and not repairable. Well, it's kind of the same question. N is still 20 because we still have a sample size of 20. The only thing that's changing here is now our number of successes is 6 because we want to have exactly 6. And their return products are defective and not repairable. So out of these, we have 45% are defective but repairable, right? 5% are defective and not repairable. So products that are defective and not repairable, that's the only classification that works. So now our P is 0.05 and our Q, of course, is 0.95. So if we go back to SAS, go back to our code, all we have to change now is, right, our p-value, which was 5%, and our number of successes was exactly 6. And now if we run that, there's the probability of that, pretty darn small, right? We go into Excel. Here's the beautiful thing of having this set up. So now our number of successes was 6. We still have 20. Now our probability is 0.05. It does everything for us. And again, there's our answer of exactly 6. And then in the calculator, we would do the same thing, except we would put in 20, 0.05, 6. And then we would run that. Okay, on to C, which is a little bit more advanced because now we have something that It's not a specific, it's a range, right? So of the 20 returned, 6 or more are defective. So n is still 20, but now x is greater than or equal to 6, right? 6 or more are defective and not functioning properly. Okay, so 5% are defective, not repairable. That is defective and not functioning. 45 are defective or repairable. That's true. 35 have small surface scratches but are functioning properly. Aha, so those don't count. So really it's just the 5 plus the 45, and now our P is 50 and our Q is also 50. Okay, so if we go to SAS, back to our code, you'll notice that this was for 1. We got to go down here for outcomes for 6 or sorry, for X or less. That's the CDF function. Now remind ourselves, we need X to be greater than or equal to 6. So you have to remember that when you're dealing with some of these technologies, they can't do greater thans. The less robust TI calculators can't do less thans. The more robust ones can. SAS doesn't do less than, or sorry, doesn't do greater than by default. And Excel also doesn't do greater than. You have to do some augmentation. So basically, the standard binomial function, the CDF, right? The cumulative distribution function is 0 up through and including x, right? So it basically gives you all of the values from 0 to x inclusive. So if you want the values where x is 6 or greater, right? So if you're looking for 6 up to whatever the max is, right? Then you need to set this x to be 1 less than that. You need to set it to 5. And then run the CDF, and it'll give you the probability of 0 through 5. Then whatever that answer is, you have to subtract it from 1 to get the piece you're looking for, the 6 and greater. Because remember, these things are complements. They always have to add up to 1. So basically, the trick when you have a greater than is you're going to have to do 1 minus the CDF, but you also have to change x, right? Depending on if it's a greater than or equal to or a strictly greater than, right? That's where you just got to pay attention to the details. So on to SAS. We're going to use the CDF, our number of trials, still 20. Our probability is now 5, and our successes are 5, right? So this is gonna accumulate all of the binomials from 0 up through and including 5. And we run that. Here's our second one, right? 25. This is what we get, but we want 1 minus that, right? So our answer would be 1 minus that. And there are ways to actually make SAS do this for you, but it's easier to just do it in your calculator, right? So just subtract that from a calculator and get, roughly 98%. Okay, speaking of calculators, if you were going to do it in the calculator, we're back down to the same thing, right? Our binomials, but instead of binomial PDF, we do binomial CDF, trials, 20, probability 0.5, x value. Again, we have to do 5 here instead of 6 because just like SAS, this is going to give us the probability up to and including 5. And then if we just do subtract 1 from it, we know that obviously, and then we know it's obviously not negative. That's just a shortcut, so we don't have to type it back in. So we know that it's 97.93 blah 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 percentage. Okay. If we do Excel, you'll notice that I've already typed these things in. Here is the formula for the binomial distribution when you want one specific thing. If you want the P to be less than X, then you can see that it's set to true, right? Same thing for X or fewer. It's set to true. True just means it basically turns it into a CDF. So if we set this to the number of successes as being 6, right, out of 20 and 0.5. Now you'll notice that X or fewer, right, that's the standard one. That's the standard distribution where it took 6, right, and took 6 or fewer. We wanted less than 6. So I wrote this to let us so that we don't have to do the changes ourselves. This function here takes C2 and subtracts 1 from it. So this is giving me the probability of the cumulative function up through including 5, which is this one. And then X or more, which is what we wanted, right? The question was 6 or more. You'll notice that it does the math for us of just taking 1 minus the answer that we got here, and there's that 97.93% that we saw that we got from our other two results, right? So in my opinion, Excel is the best way to do these, but sometimes some schools, some professors require you to do them other ways, so that's why I'm showing you all 3 ways. Okay, this video is getting kind of long, so I'm going to do the next part of this question, and then I'm going to stop there, and I'm going to post a second video for the second question. All right, so none of the 20 return products has any sort of defect. This one should be pretty easy because part D, right, N is still 20. None of the 20 return products has any sort of defect. Well, if you look at all of this, that's just 15% have no problems. So again, we're back to x equals 20 because all of them have to have something. The probability of that success is 0.15. Of course, Q is 0.85. You'll notice that we've never needed Q for any of these things. We would only need Q if we were using the formula. So back to SAS. Do SAS first, back to our code. This is a single thing, right? It's all 20, so we're using the single outcome of 15%, and all 20 of them are good. Run this, and there's our teeny tiny example, right? Negative 17 means you got to move this over, and then there are 16 zeros in front of it. Let's try it in the calculator, see what happens there. Binomial PDF, 20 trials, 15%, 20 successes, paste that, run that. You see the same thing, right? A lot of zeros. And then if you do it in Excel, of course, you're going to get the same thing. 20 successes, 0.15, and you can see that it gives you exactly that many successes is 0, and the only way to actually see where it is, right, what the number is to keep giving yourself, there we go. We can finally see where that number is, 16 zeros and then some numbers. Okay, so that's how we tackle basic binomial distribution questions using either SAS, Excel, or the TI calculators. Come back for my next one and I'll show you how to do the second question along with the Poisson approximation.